Start the recording and we're ready to go. Good morning of October 22nd. I hope everybody's doing well. I hope you're enjoying the cool weather. I don't know what it's like where you are, but it's nice and cool here in Camarillo, Southern California. Yeah, so I'm enjoying it. I got my windows open. I'm sorry if you'll hear sounds of my neighbors washing their car or whatever, but it's a reminder that I'm in a very similar situation to you. We're all in different kinds of situations. I see comments in the chat. Is there homework they're supposed to be working on right now? I just posted homework to Canvas site on some material that I'll talk about today. And in the R file that I just distributed through Canvas, at the very end, there are two data sets that I hand typed in there so you don't have to type them in. And I think that's for problems from 1.2. So just be aware. There's the problems in 1.3 where you will have to type stuff in. I figure it's good for you to have some experience doing that. But just be aware that I've created some data sets for you in that R file that you can take advantage of. All right, so today we're going to talk about something interesting for a change. We're making that pivot that I promised to statistics. And statistics is the practice of studying populations.
I found this on the web.
Oh, thanks, Siri. Studying populations by looking at subsets of the populations by taking what are called samples. And so I want to talk about that a little bit today and then review some basic stuff about statistics that will kind of retread some stuff that we talked about in probability. So you'll see how there's a big overlap between the topic of statistics and the topic of probability. So you'll get to reuse a bunch of what you've already learned this semester and put it to use. And we'll get an opportunity to start flexing some of our R skills too. And I'll try to model that using that script that I sent out by email and posted to the Canvas site. So yeah, what we're going to talk about topics in chapter 1 today, and if things go well, I guess if things go the way I planned them, they could still go well, and they don't go the way I planned them. If things go the way I planned them, we'll get through the first 3 sections of chapter 1, and then on Tuesday we'll talk about chapter 3. So in preparation for Tuesday, start taking a look at chapter 3. We'll go through it more deliberately than chapter 1 because a bunch of the stuff from chapter 1 you've seen already. All right, so I've shared my iPad screen, and seem to have gone to sleep on me. Now it's back. Okay, so statistics. Statistics is the study of using data to understand phenomena. And oftentimes the way we understand things is by making observations and making measurements. And a lot of times when we're trying to understand something that's really big, we can't observe everything that's in that population or in that collection. We can only observe some of it, or we can only make measurements of some of it. Okay, so although we want to understand a whole phenomena, of a population, we can only, or we only have access to a sample of it, or okay. So if I have this big circle representing a population, we might only be able to take a slice of that population, okay? And so statistics is the study of taking measurements from what we can see and extrapolating the patterns we see to patterns of the whole population. Okay. So how to measure a sample of a whole population and extrapolate the patterns we see to the whole population with confidence. All right, and so that last underlined statement phrase, with confidence, is an important part of statistics, right? Anybody can look at a subset of a population, see patterns there, and jump to conclusions that those patterns must be occurring in the whole population. But we can look around us today in America or in the world and see that there's lots of people that do that, and they the conclusions they jump to are pretty fishy. In statistics, we want to make sure that when we make that extrapolation or make that inference, that we do so in a way that we have confidence in and that other people can have confidence in. Okay, and so the first thing that we have to do as statisticians is make sure that the way we're choosing this slice is gives us a good sample. If you're trying to make an inference or an extrapolation about some pattern to a whole population, and you have no control over the slice that you get, you cannot make those extrapolations with confidence, okay? You need to know something about how this slice was obtained before you can do anything with confidence. Okay, so I want to talk about a little bit about how we do that, okay? So let's see, just for the sake of having a conversation, what's a population that we might be interested in studying? Anybody? I guess it could be, you use the word population, it makes you think of people or it makes you think of animals, but it could also be, it could be anything. Is there any?
People with the coronavirus.
People with the coronavirus. Okay. All right. Sure. Okay. So people with so people that have the virus that causes COVID-19. Say that's the population that we want to understand. Well, that's a great population to choose because we don't exactly know who's in it, right? The virus, yeah, we don't know. Testing is ineffective. So even if we could test, even if we could test everybody, we know tests aren't entirely effective. So we can't have an objective way to know if we got all the population in there. We know what the whole population is, but we can look at the people who have tested positive and say, yeah, they're going to be in the population. So yeah, this is an interesting population to have. So how would I take a sample? What's the best way to get a sample of members of that population if we were to take some sort of measurement of them? And here's the, does anybody know the best Method for getting a sample? Anybody know?
Is it just random?
Yeah. It's called a simple random sample. The best sample you could take, and I'll tell you what I mean by best. Okay. The best sample you can take is a simple random sample. And that's where you take a list of everybody in your population, in this case, everybody who has the virus, and you randomly choose people from that list. And we've got R, it's got a random number generator. And so you can have it make the selection for you. Okay. So maybe the first thing you do is you choose the size of the sample. And we'll call that capital N. And how big N is, there's an art to choosing how big N is. And we'll talk about that in the class down the line. But say it's going to be 100, say it's going to be 1,000. And then you take a list of all members in your population. And say it's an ordered list. And so you can give every person in that population a number. And then use R to say sample. And let's say there's 1 million people who have the virus. You can say, I'll take that, the numbers of all the people that have the virus, and I'll choose N. And I don't want R to replace anybody. Once I pull somebody off the list, I want to keep them off the list. So that way I know I'm getting N different people off the list. Then this command will give you a list of length N of different people that you've numbered. And then you can go back to the list and look at the people who have those numbers. And there you go. You've got a simple random sample. Okay. And I'll show you an example in R about how to do that. So I'll show you explicitly how to do this. Maybe I should do that now. Let's do that now. So I'm going to share R with you. See if I can find it. There we go. RStudio.
Professor, why do we sample from a list of numbers rather than the list we wanted to sample from?
Why do you sample from a list of numbers? So, what would your list be? I'm just curious. What's in your mind? What are you thinking of your list?
So we have that list of people, whether that's their names or the data we want about them.
Yep.
I think where you have 1:1,000,000, you could just put that list.
Say that last sentence again. If you have what?
Where you put 1:1,000,000 in your R line, I would think you could just put whatever you would call the list.
Yes, and I'm sort of doing the same thing, because if I've got a list, it's got an order, and that 1:1,000,000, that's meant to be the numbers in the ordering. So even though you've got a list of, say, social security numbers, I'm going to put those in an ordered list so I know what the first social security number is, the second, the third, the 500,000th, the 751,829th, right? I know where they all sit on the list. And so I choose a subset of the indices, and that tells me which social security numbers to choose. Does that make sense? It's like a lookup list.
Okay.
It's like a lookup table, right? Okay, so I've shared R. So here I've got a little section in my R script called sampling from a census. Can everybody see it? Everybody good?
Yes.
Anybody have any problems? I'm looking in the chat, trying to get it visible here. Oh, Kevin asked about the lecture notes. I think the Canvas site should be all up to date with the video and the lecture notes. So take a look at that. So back here to the RStudio, line 6, I'm creating a fake list of identification numbers of six-digit identification numbers, a list of 100,000 identification numbers. So this is like, think of them as social security numbers or student IDs or something. So I can create those, and I'll calculate the length of the list that I generated with the command on line 7. And you can look down in the console, you can see, yep, indeed, that list has 100,000 things in it. And let's just double check. Oops. Throw in the console, ask it to show me what the ID numbers are. And R will kind of puke. It stops after 1,000, but you can see here's a bunch of 6-digit ID numbers. On line 10, I'm going to take a list. I'm going to make a list, which is my sample, a sample of 100, size 100. And I'm picking numbers between 1 and 100,000 because 100,000 is the length of the list of ID numbers. So those are my indices, these 100 things I'm going to choose. So let me choose those. So I just created a list, and I'll look at that in the console. Let's see here. There's a list of a bunch of numbers between 1 and 100,000. And so this represents my sample, the sample I'm going to choose from the list of ID numbers. And so command 12 is the money command here. I've got the name of my list of ID numbers, and I put in square brackets my list of indices, my choices. And so if I execute line 12, you'll see down here in the console, I just got a list of 100 different ID numbers of length 6 or 6-digit ID numbers. So this down here in my console would represent the sample I chose from my list of 1 million ID numbers. Okay, so this is how you can get R to do your simple random sampling for you. And in R, it's this sample function right here that's making your sampling. So what makes simple random sampling so good? I mean, when I was first learning about this, I said, well, this is so dumb, right? It's so simple. Isn't there something more sophisticated? Isn't there something that has a little bit more intelligence or thought that goes into it? And the answer is no. This is it. This is the best way to sample. And why best? And the reason it's best is there's no bias. Okay. Having the computer make the choices for me, there's no bias. Okay. And what kind of biases can there be? Can somebody give me an example of a bias a person might have when they're choosing?
When you ask people for a random number between 0 and 10, you'll get a whole lot of 7s.
Okay. Yep, so people are bad at choosing random numbers. Okay, so that's a numerical bias. Okay, good. Anybody else have an example of a bias?
Only choosing like from one page of the list if you're doing like a physical list.
Yeah, right. Okay. Laziness, right? Only choosing from a part of your list.
People don't have long enough runs in random coin flips that they simulate in their heads.
Okay, again, that probably goes back to biases about choosing random numbers. So you'd say if I chose person 100, I probably shouldn't choose person 101. Right? That's kind of what you're saying, Patrick, is that they're not allowing for themselves to choose clusters of things. So I'll put that in this category. People are bad at choosing random numbers. Other things that other kind of biases that one might see in a statistical study?
Location bias. So they only sample a specific location instead of the general type of,
Yeah.
for example, in in the United States, they would only sample a specific state when maybe they want everyone across the nation.
Yeah, that's right. Sure. There might be a location bias. Uh-huh. Good. I'll try to come back to that. But thanks. Other biases?
Well, if you have one over the phone and then like the people you call, if they work and they can't answer, so that would be like on their time with when you're calling.
Yeah. Right. So there's okay, I'm gonna call that an availability bias. And that might happen when you after you've chosen your sample and when you're trying to gather your data. But you're right. If you only make your calls at noon, there's a bunch of people you're never going to contact, right? If you only make your calls at 6, right? Somebody who's got a family and they have family dinners, they're not going to pick up the phone, right? So this plays into what I might call experimental design. And what it does is it leads to a bias. The way you carried out your experiment created a bias in your data. So, but that's a good observation. Was that you, Haley?
Yes.
Okay. What other kind of biases could be introduced into a study that simple random sampling protects you from? No others?
Doctors in particular, will choose patients they think will benefit from something if they're trying to prove that the thing works.
Yeah, so outcome bias. If you know something about people in the population, you might be predisposed to choosing people that are more likely to give you the outcome you want. Yep. Any other biases?
Maybe like a medium bias, like you're less likely to get elderly people if you like interview over the internet.
Yeah, so an age bias. Yep, I mean, and that could relate in some ways to outcome bias depending upon what you're doing, but there could be an age bias. And again, that might relate to, since you bring up the internet, that might be related to experimental design too. And so it would be a consequence of how you do get the data.
Self-selection bias.
What does that mean?
If you let people volunteer to take a survey, you're going to get different results.
Oh, yeah, that's right. Yep. So right. And so I'll talk about one type of sampling method that has that flavor and really sucks. So there are 2 other types of bias that I want to make sure that's on the list. And one of them is a gender bias, right? If you know the genders of the candidates, for some reason or other, you might get a sample that's biased either for or against one gender. Racial bias, right? You might include or exclude people based on the basis of their race. And you can think of any other sort of divisive topic, politics bias. If you're for Trump or for Biden or for the libertarians or whatever, and you know how people feel about those things, right? That could introduce a bias. So a lot of these things in the list are you're insulated against these kinds of biases when you use simple random sampling to select your sample, right? You let the computer do it, right? And you don't take anything else into account except the members of your list, your members of your population, and let the computer do the work. Okay. So let's think of an example, another example besides different from COVID. Suppose you want to know the average height of students that attend Channel Islands. Okay, and so your population are all the students that attend Channel Islands. So and you decide that you want to select the first 10 people that you see at a residence hall. Is that a good selection method?
No.
Okay, Patrick says no. How many people agree with Patrick?
I agree with him.
Anybody else? Ashley does. So if you agree with Patrick, think for a second, why is that a bad selection method? What kind of bias does it have? Okay, how might that sample be biased?
I would expect the people who live in residence halls to be younger and therefore marginally shorter.
Okay. Anybody else have a thought on what kind of bias taking a sample at a residence hall would have right now? No? So I think Patrick's point is a good one, right? They'd be younger. I don't know what effect that would have on height necessarily, but it certainly would increase the likelihood that the people that you encounter at a residence hall would be younger.
I expect you'll see some gender bias. I don't know the direction, but it would surprise me if there wasn't any.
I guess it depends upon where in the residence hall you waited, right? I mean, depends upon like the population of the residence hall. But what about socioeconomic status? Right now, what kind of people are in the residence hall, do you think? People that can afford it, right? And so there's probably a socioeconomic thing happening if you're waiting at a residence hall. Are these biases that you're intentionally putting into your data? No, they're not. You're not intentionally stacking your deck with those kind of biases, but they're unintentional biases that are that your data set inherits. Okay, because you wanted just to take the first 10 people you saw at a residence hall next week. That kind of sampling where you just show up someplace and take the first 10 people is called a convenience sample. And it's called a convenience sample because it's convenient for you, the person who's collecting the data. And convenience samples never give you good data. Sometimes convenience samples are a good way to get pilot data just to see how your experiment's going to work. And then maybe the next step after you get that convenience data is to create an experimental design that guarantees that you have a wider variety of data in your sample. So I'm just making a note. This example of the first 10 people at a residence hall, I'm going to call that a convenience sample. And that's bad. Okay. I mean, you're not a bad person for doing it, but it's going to introduce bias into your sample. And you don't want that, because that means that your sample is not going to be representative of the whole population of all CI students. Yeah. So in statistics, one of the things that we study is variation. Okay, how data changes. I mean, even this idea of a variance that we talked about. The variance is defined to be the sum of the differences between a value in our data set and the mean, right? So this is called the variance. And I guess we can put this here too. In statistics, often what you're trying to get at is why is there variance? What is the source of the variance? Let's say variation instead of variation. Because we all want to think of processes in the world as being like mathematical functions. You've got independent variables and you've got dependent variables, right? And if you can set up an experiment so you can see the independent variables moving around, and then you can look at the dependent variables moving, then maybe you can deduce how the independent variables and the dependent variables are related to one another, how the variance in one affects the variance in the other, right? That's the idea of statistics. If you take a bad sample, if you have bias in that sample that you're not aware of, there's no way you're going to get a good bead on how the sources of variation in your data. If you're ignorant of a variation that you baked out of your data because of your you took a convenient sample. Okay. So there's a couple types of specialized samplings. Okay. So simple, random samples. In theory, theoretically, they're the best. Okay, because they kind of get rid of all the bias. But sometimes you need to be sure that you're getting important sources of variation in your data. And I think of like a medical trial. So back to COVID, think like vaccine trials. When, let's see, who like Johnson & Johnson or Pfizer, when they're doing a vaccine trial, they get a bunch of people that are willing to be in the trial, right? So they have to give consent that they're going to be in the trial. And a trial is like an experiment. People know how these vaccine trials work? In rough, broad strokes?
I mean, I'd guess that they're double blind.
Okay, double blind. What does that mean?
It means that the participants don't know whether they're getting the vaccine or placebo, and neither do the doctors running the experiment.
Yeah. So I wanted to get at the vaccine and the placebo, right? So these are called factors. So having a vaccine and a placebo, that might be called a two-factor vaccine trial. So all the people in the trial get either a vaccine or a placebo, and it's a single blind experiment if the participants, the subjects, don't know which one they got. And it's a double blind if the experimenters, the medical scientists, if they don't know too. And one of the reasons you blind an experiment is because you don't want to introduce bias, right? Conscious or unconscious bias. So the blinding removes bias. A person getting the placebo, right? There's this thing called the placebo effect. Even if you know you're getting the placebo, well, no, I guess that's the placebo effect is if you think the placebo is effective, it's going to have some effect on you, right? And so in a trial, you want to allow the placebo effect to have some effect if you believe in it. And then the double blind removes the bias of the experimenters. Okay, so if it were as simple as this, you could do a simple random sample, right? You get a simple random sample of everybody who is worried about COVID-19 and wants to participate in the trial. And then you can take your sample of those people and divide them up randomly into the two experimental groups, the vaccine group and the placebo group. But this isn't good enough. This is not how we do them. Maybe 50 years ago, this is how we would do them. But today we know that we need to learn effects not just on white men, but on women. And not just on white men and women, but on Black men and women, Latinos, and other people of color, right? So how do you guarantee that your sample has members of these populations that you want to see how the vaccine affects them? Well, one way you can do it is you can just say, I'm going to take a big ass random sample. So I'm pretty certain that I'm going to get a wide variety of people in my experimental groups. Okay. But that's not good enough. I mean, you're still at the mercy of randomness. So what people do to make sure that they have represented in the experiment those subpopulations, I'm going to call these important subpopulations. So if the whole population is represented by the circle, then say there's some subpopulations here, and let's say my horizontal lines are like primary ethnic background, and let's put a line like this. So we have males and females, biological males and biological females on either side. Okay. So these are called stratifications of the population. And I've got two independent stratifications, one based on biological sex and another one based on primary ethnic background. And so what you can do is as a researcher, you can say, I'm going to take a sample of one of the sexes and a sample of the other sex, and those samples are called a stratified sample. Oops. Okay. And what you do is you say, I want to make sure that I get a certain proportion of my sample from this one strata, another proportion from this strata, and another proportion from these other strata, and likewise over here. So you divide the whole population up into these groups, and you just make sure part of your sample comes from that strata. Okay. So this is one aspect of thoughtful experimental design, is to understand your population, how it subdivides into subpopulations that are important for your study, and then how do you divide your sample between them. And then within each of those subsamples, you use simple random sampling. Okay. So on the one hand, you're trying to make sure your samples have a fair bias about the way your population is structured. But beyond that thoughtful experimental design, you want to make sure the choices inside of each of the strata is random. And so you're removing all other bias. That way, it's in that sense that your sample is representative of the entire population. Because what if Pfizer had a bunch of people in their trial and there were no white women? That would really weaken their results. That would really make their results poorer. What if there were no Black men? that would make their results poorer. So they want to make sure that they can get the information about all the different aspects, all the different kinds of people that live in the United States, for example, since we're talking about Pfizer, or the world, right? Their strata, their population might be the world population. So simple random samples are the best, but sometimes you need more structure in your sample. You need the guarantee that it has more structure. And so there's a way of creating what are called stratified samples that rest on the principle of simple random samples, but they give you the kind of data and the variety of data that you need. Because if statistics is about variation, there's some variation you want to make sure your data has. And stratified sampling does that for you. Well, there's one other type of sample that the book mentions. It's called cluster sampling. And so I forget who mentioned it. Somebody, one of you talked about, maybe it was you, Daniel, about geographic sampling.
Yeah.
So if you were doing a study and you wanted to take a sampling of people, and your sampling required interviewing people to ask them questions, and it was a national study. Okay, so here's my bad picture of the United States. If you need to interview people, right, you've got to send interviewers around. And so maybe you send somebody to LA, maybe somebody to Seattle, maybe somebody to Minneapolis, maybe somebody to Washington, D.C., maybe somebody to New Orleans. But then when they do their interviews, they're only going to catch people that are in the vicinity of where they're interviewing. Okay. These different regions would be called clusters. Right. Even if you're going door to door asking questions, even that process of being limited by your foot, able to walk different places, that creates a cluster of your sampling. It's not reasonable for you to say, "Hey, I'm going to take a simple random sample of locations across the United States, and then go send somebody there to survey them." That would just be too expensive in time and money. Nobody would create an experiment that way, even though it would be ideal. Sometimes our ideals fall to some of the wicked truths of reality. So cluster sampling, maybe not the best, but if you can spread your clusters around, maybe that would make them better. But if you only put a cluster in New Orleans and you expected to extrapolate the results of that survey to the rest of the United States, that might be problematic, because the population down in Louisiana is different from the population in Southern California, different from the population in the upper Midwest. So cluster sampling, you just got to be careful. It's a natural thing. A lot of people do it, and people understand its strengths and its weaknesses, but it does have strengths and it does have weaknesses. So I'm glad you brought that up, Daniel. All right. So when you do statistics, you're collecting data, and data really falls into two types: qualitative or categorical, and quantitative. The second of these, quantitative, basically think of it as anything numerical. Okay. Anything that comes about by some sort of measurement. It could be a count. It could be you weigh something. It could be that you measure a length. Right. Quantitative is something that we in the mathematical sciences do all the time. Computer science, mathematical sciences, right? Statistics. I think nobody in this class is going to have a problem understanding what a quantitative data is. So let's talk for a second about qualitative data. Can somebody think of something we might measure that's qualitative?
Political affiliation.
Sure. Political party. Good. Something else?
Would gender be categorical?
Sure. Gender would be categorical. Even though a lot of people say it falls on a spectrum, so you could, but nobody figured out how to assign numbers to it, so that we'll say gender is categorical. What's something else?
Grade received.
Let's say letter grade, because we know how to give letter grades numbers. So you could, somebody could be a little snarky and say, "Hey, my GPA is a number," but yeah, like a letter grade A, B, C, D, or F.
Especially if you include W, it's qualitative.
W's. Hair color would be a qualitative variable, a qualitative quantity. No, I don't want to say that. A qualitative thing. Let's call these variables. Types of data, types of variables. Blood type. That's categorical or qualitative. Eye color. Primary ethnic background. Species. Like if the population that we're interested in are all of the mammals that live in the Los Padres wilderness, for example. We could say that you find a mammal and you say what's its species, and that becomes one of your variables. If we're talking about cars, we might talk about the manufacturer. We might talk about the make of a car. But if we talked about the year a car was manufactured, then that would be quantitative because it's a number. All right. You get the idea? Quantitative variables, qualitative variables. In this class, we're going to have lots of tools for playing with quantitative variables, but qualitative variables are going to come up. Okay. Qualitative variables are going to be something that we're going to want to be able to understand too. So keep that in the back of your mind. A lot of times, yeah, so here's a good thing. What color should I use? I'll use light green. Qualitative variables are always discrete variables, right? There's always a finite number of categories. But quantitative is the only one that can possibly be continuous. Okay. There's no such thing as like if you had a random variable that was describing a quantitative or a categorical variable, then that random variable would be a discrete random variable. But if you had a random variable that was describes a continuous quantity, then that has to be a quantitative quantity. Okay. All right, so that was section one of chapter 1. So let's move on to 1.2, and so this is going to feel like a little reprise of stuff we've already talked about. And I think the book calls this summary statistics. And maybe a theme would be how to describe samples with numbers. Okay. So what we're going to do is talk about ways that we can take a sample of measurements. I'm going to call these univariate data sets. Okay, so there's only one variable that we're measuring. Okay, so we're just going to have one set of numbers. It's going to be one vector. Or one set of numbers. So we've talked, so what are some ways that we've talked about measuring lists in this class so far?
Mean and standard deviation.
Okay. We've talked about the mean. We've talked about the standard deviation. Is there anything else that we've talked about?
The size of the list.
Sure, size of the list. How many things are in the list? Can somebody, other than Patrick, tell me, what does the mean measure? What does the mean of a list measure?
The average of all the values.
Yeah, but what is that a measure of? Because oftentimes mean is the same thing as average.
It's the expected value if you chose a random.
All right, you guys are throwing around good nerd words, but what is it measuring? For somebody who's just coming to visit class today for the first time, what would you say the mean is measuring about a data set? What is it telling us about the data set?
The middle?
The center, the middle. Okay. The mean is telling us where the middle of the data is. Okay, that's the measurement that we're getting from it. How about the standard deviation? What's the standard deviation telling us?
The spread of the data with
Yep.
relation to the mean.
Yep. So the standard deviation is telling us how the data is spread out around the mean, around the center. The size is obvious. A couple other measures that we can make are the minimum and the maximum of the data. I guess one thing that we probably could have measured, I'll do it in dark gray here. Standard deviation is related to variance. Okay, so variance is the square of the standard deviation, so it's also telling you something about the spread. Okay, let me give you a definition here. So let the set x1 through xn be a sample of measurements from a population. And I don't know what I'm going to call it. I don't think I'm going to have a notation for the population. But then we say, then the sample mean, okay, not the mean, but the sample mean is denoted x bar, and it's the average of the numbers in the list. Okay. So familiar formula, new notation, new name. Okay. So we'll contrast this with the population mean, which we call mu. And that's what we talked about in the first part of the course, the mean of a random variable. Now we're talking about working from the other side of this coin, that is statistics. where we only work with samples, and you get a sample and you can calculate the mean of that sample, and we call that the sample mean. Okay. And the idea is, if the sample is a good sample, then the sample mean is approximately equal to the population mean. But the population mean isn't something that we can we can't calculate that directly. We can only calculate that through a sample. And if our sample is good, then our sample mean is going to be close to that population mean. Okay? And here is our entree into doing statistics. The question in statistics is, what is the difference between the sample mean and the population mean? And how can we make that distance, that difference, small? Okay. Yeah, so I'm trying to think if I should show you something with R right now. We're at 11:30. We got 15 minutes left. Oh dear. So what I'll say is, we can say a similar thing with the standard deviation. So if we have our sample, from a population, then the sample variance is this quantity, and I'm going to call it S squared. That's the sample variance. Now, variance, population variance would be sigma squared. Okay, or var. So in statistics, what we're going to do is we're going to use a lowercase s to be the sample version of a standard deviation. And when we calculate a sample variance, it's very much like the formula for variance. So let's see, formula for variance was the sum over the x's in our sample space of x minus mu squared probability x. So you can see one of the differences is, because we're working with samples and we don't have access to the population mean, we only have our sample mean. So we use the sample mean in the formula for variance. And when I was first learning this, I said, well, why are we dividing by n minus 1? Well, it turns out that this n minus 1 makes the sample variance an unbiased estimator for the variance. Okay, or maybe I'll just do this for the variance. What that means is, if we divide by n minus 1 instead of n, most people would say, why aren't we dividing by n? If we divide by n minus 1, then this difference over here between s squared and sigma squared is going to be smaller on average than if we divide by n. Why is that? I'm not, that's sort of beyond the scope of this course. What we need to know is just that when you're computing the sample variance, divide by n minus 1 instead of n. It's one of those little facts we just have to keep in our mind. All right, are we ready to go to R? There's one more thing I want to tell you before we go to R. There's another way to measure the middle of a data set, and that's called, another measure of the middle is the median. Okay, so to get the median, what you do is we're going to take our list and we're going to reorder. So xi is less than or equal to xi plus 1. Okay, so our list becomes an ordered list. And then what we're going to do is that we're going to, but I like to think about it as working in from the outside. So first, like chop off the biggest and the smallest, and then chop off the remaining biggest and the smallest, and keep doing that. And either you're going to end up with a single number, xm, and then that's what we call the median. Or you're going to end up with nothing. And you end up with nothing when you've got an even number of data points. So if that's the case, then the previous or the last points to be dropped were xj and xj plus 1. They were two adjacent data points. And so what we're going to do is we're going to take their average, and then that's the median. So the median is literally the middle of your data set when you list your data in order. And then if you've got an even number of points, you have to pick a new point. You have to make up an imaginary point that's between them. So it's in case 2 that your median isn't actually in your data set. But in case 1, when you have an odd number of points, your median is actually going to be a member of your data set. So you need to know how to calculate a median. You need to know how to calculate a mean. But most of the time, you'll just make R do it. So I'm asking you to be smarter than R, but I'm also going to ask you to do almost all your calculations in R. So let's go and look at R. And so I'm going to look at this next example called sample statistics. And what I'm going to do here on line 19, this is a way for me to just set or control the random number generator. And so each time I execute line 19 and then execute line 20, even though I'm choosing 1,000 random numbers, because I set the seed in line 19, I'm always going to get the same 1,000. So it makes it predictable. So let's do that. I'll set my seed to 124. I'm going to create a data set A that consists of 1,000 random numbers between 0 and 1,000 random numbers that come from a normally distributed random variable with mean 0 and standard deviation 1. We talked about that last time. So line 21, I'm going to calculate the variation or the variance of the data set. So look down here in the console to see what it calculates. Well, no, here, let's do this first. The mean. Let's calculate the mean, line 23. Hopefully it'll be near 0. And there we go, negative 0.06. That's very near 0. Now I'm going to calculate the median, negative 0.08. Also very close to 0. So the mean and the median are very close to one another. They're both measures of middleness, of centerness, so we expect them to be close to one another. Let's calculate the standard deviation. My random variable that generated these random numbers has standard deviation 1. Let's see if our standard deviation is close to that. 0.978, very close to 1. And now variation, 0.9569, also close to 1. So in this example of line 20, you can imagine my population is the population that's described perfectly by a normal distribution with mean 0 and absolute or standard deviation 1. and I created a sample of a sample of size 1,000 from that population. And then here I calculated my sample mean, sample standard deviation, sample variance. Watch what happens if I make the size of my sample smaller. My mean, oh, it's still close to 0. That's great. My median, yeah, that's still pretty close to 0. Variance is a little bigger, and standard deviation is a little bigger. So this is how you calculate mean, median, variance, and standard deviation with R. Here's a similar example, but I'm creating a data set by sampling uniformly from the list of 1 to 20. So this is a uniform distribution and I'm sampling 75 values. And I'm allowing for replacement, so I could sample the same number several times. So the mean of this set is 9.6, and I expect my mean to be 10. The expected value of a uniform distribution from 1 to 20 is 10. The median is exactly 10. So this is all checking out. This is all looking good. The variance is 37. That's interesting. That's huge. The standard deviation, this should be, yeah, is 6. Yeah, of course, it's the square root of the variation. So let's look at this example here. I've got an explicit data set here. Here's the numbers in my data set. Some numbers are repeated. I'm calling the data set C. The mean is 1.5 and the median is 1. They're not exactly the same, but you could say, oh, they're close to one another. It turns out the mean is what we call sensitive. It's sensitive to outliers. So what I'm going to do next here is I'm going to create another data set, C2, but this -10 here, which is on the end, it's the minimum right here. I'm going to replace it with -40. So I'm going to move it way down to the left on the number line. So you can say down here, the console, C2, the data set, it's exactly the same, except I made the smallest member a lot smaller. So let's compare the median of the original data set with the median of the modified data set. So the original median was 1, and the new median is still 1. So making that change to the data set didn't change the median, which is interesting. Now let's look at the mean. The mean was 1.5 before the change, and after the change, the mean now is -0.6. So the mean decreased by 2. This is what we mean when we say the mean is a sensitive statistics. The mean is sensitive to outliers. So small changes in the data should only give you small changes in your statistics. But the mean is affected by outliers, things that are out on the edges of your data. And so that's just something that you need to remember. And this is an example that shows it explicitly. And because the standard deviation is the mean of your variances, or the square root of the mean of the variances, that is, a standard deviation is a mean, it too is sensitive. It's a sensitive statistic. So the standard deviation of the original set is 4.5. The standard deviation of the modified set is now 11.8. That's a huge change just by changing 1 point in the data. So remember, the mean, though easy to calculate, is a sensitive statistic. The median, a little harder to calculate because you got to sort and count. It's not sensitive. We might say it's insensitive. But why am I complaining about how hard the median is to calculate? We've got R. It'll do it for you. So don't have to worry about that. All right, we have 2 minutes left. The next thing I wanted to talk about, let me scroll down in the R file. So you can see here's the next topics. Tiles, I'm abbreviating here. So they include percentiles. Let me draw a picture and then we'll call it a day. I'm going to go back to my iPad. I'm going to draw kind of a number line here. So say you've got a data set and it's got a minimum here I've denoted and a maximum I've denoted here. If you calculate the median of your data set, by the definition of the median, 50% of your data lies to the left or to the right of the median, and 50% of the data lies to the left. Okay. So you might call the median your 50th percentile, because 50% of the data is below your median. Well, using that idea, we can define quartile. So I could define a number here that's the 25th percentile, meaning that below it is 25% of the data. So above it, between it and the median, there's 25% of the data. And likewise here, I could say there's 25% of the data here. These blue numbers are called quartiles, okay? And they are numbers that represent how distributed your data is. So standard deviation and variance give you one measure of how things are spread out. Quartiles give you another method that they're spread out. And we could even go further. We could talk about percentiles, right? So you could pick an arbitrary percentage, like the 38th percentile. Let me do this in a different color. I could ask, what's the 38th percentile? That is, where on this list do I know that there's 38% of the data is below it? Right, that's a percentile. All of us who have taken standardized tests, are familiar with this, right? If you're at the 90th percentile, that means 90% of the other test takers were below you. If you're at the 80th percentile, 80% of the other test takers were below you. So I'll start here next time, and I'll show you how R calculates these percentiles for you, and I'll show you how we can use that to visualize the shape of the data too. So play around with the R file that I sent to you. Some of it might be helpful for the homework. The homework, I want you to do some of it by hand and some of it using R, and I've tried to be very clear about which problem is which. All right, thanks for letting me go over for a little bit. I will post this stuff to the Canvas page right away. And I'm pretty sure everything there should be up to date. I've made sure that some people sent me some email that it wasn't working, and I think it should all be working now. So if I'm mistaken, just send me an email, let me know. I'll fix it this afternoon. Okay, thanks everybody. Stay well, stay healthy.
Thanks, Dr. Miller.
Thanks, Dr. Miller. Bye.
Yep, see ya.